Um, my name's Ken Hausman. I work for Greenman Peterson, GPI, in their Lebanon, New Jersey office, which is in the northwest part of the state. My topic today is modeling New Jersey Route 495 and the exclusive bus lane, the XBL. I had an opportunity to present at the 2018 users group meeting up in Toronto. And I guess someone also in attendance there, so great. And where I talked about a different interchange in New Jersey, but whereas that project was really focused on the alternatives analysis and some of the features in VISM and trying to take advantage of them, this project is really focused on modeling the MPT scenarios. Okay, I'd like to say thank you to the client and the people at GPI who picked up the tab for me to be here. Dr. Sayani from the Turnpike Authority, who was the Turnpike project manager, Sean Reichel, who was the GPI project manager, Bernie Borchers, who's the director of transportation, and Brian Mauser, who runs the New Jersey operations. One of the things which I really enjoyed about this project, and I've only been with GPI since 2019. Before that, I was a sub-consultant. I worked with GPI on a bunch of projects, but I really never got brought into doing the MPT analysis. It was always for the alternatives analysis, and it was great to be integrated into developing the MPT and working in a really collaborative, I'll say virtual room, as opposed to the old-fashioned type, with the structural engineers and the civil engineers and the construction people and everyone else. Okay, let me talk about the project that started it all here, which is it's a structural project. It's replacing two bridges on the Turnpike Authority. Interchange 17 in the picture, just to try to orient you a bit, southbound on the Turnpike is to the bottom and right. This project, as I had mentioned before, the focus was not on the alternatives analysis, because this project was about taking two-lane bridges that I guess are 60 years old now and functionally obsolete, and replacing them with two new two-lane bridges that were going to be located either just outside the existing bridges or just inside the existing bridges. So really not much traffic modeling work for the alternatives. The traffic modeling work was going to be about maintaining traffic, and I'll use the term satisfactory traffic operations, but it's northern New Jersey. Satisfactory traffic operations during certainly the morning peak period is level of service F conditions. Okay, so not everybody is familiar with the area. Interchange 17 in the center there is the exit that connects Turnpike southbound traffic to Route 495. Route 495 is the road that then connects to the Lincoln Tunnel into New York City. Route 495 is also where the exclusive bus lane is located. And right there where 495 comes into Manhattan, that's the location of the Port Authority bus terminal, which the combination of the bus terminal, which is scheduled to be redeveloped, the tunnel, the Helix roadway, which is this lower speed spiral roadway that connects the elevated 495 down to the tunnel entrance. All of these things are capacity constraints in the existing network. Let me also just kind of throw a couple of statistics here about the level of traffic that we're talking about. Pretty much these roads that I've highlighted here carry over 100,000 vehicles per day. 495, Route 3, which is the connection to Western New Jersey. The Turnpike is actually two separate roadways here. The Eastern Spur on the east side of the Hackensack River, and then the Western Spur on the west side. The peak traffic, not surprisingly, is toward the city in the morning, but the traffic patterns are really surprisingly balanced, especially in the evening peak hour, where New York City just draws so much visitor traffic that in some ways the kind of learned, having pretty much lived here most of my life, that driving into New York City in the evening is not something that you want to do if you can avoid it, because you're going to sit in pretty much as much congestion as if you were driving in the morning. Although a quicker ride home when you're coming back at midnight in the evening. All right, let me talk about a few of the project challenges. Again, the need to maintain operations for both the Turnpike and the exclusive bus lane during construction. I always liked this graphic because it really highlights the challenges because of the multiple agencies involved. The DOT, their roadways are shown in red. That's Route 3 and Route 495. The Turnpike is shown in green. Hudson County, where this is located, certainly has a significant presence here. Patterson Plank Road there, cutting through from northwest to southeast. And the exclusive bus lane is actually operated by the Port Authority, who also operates the Lincoln Tunnel and the bus terminal in Manhattan. All right, let me talk a bit about the exclusive bus lane. There's the bus lane in the picture on the right. The bus coming towards you, that's the exclusive, that's the XBL. So it operates in the left lane on the westbound roadway. The bus lane, they actually shut the roadway down at 5 a.m. to make sure the road is cleared. Buses can use it from 6 to 10 a.m. It opened in 1970, pretty heavily used even back then. 9 million passengers a year. 2019, 1,850 buses per day, 18.5 million passengers per year. And the estimated travel time savings versus general purpose lanes, 15 to 20 minutes. Now, one of the things which I'm going to be talking about later, but you can see it, I think, fairly well in this picture, that this is the morning and you see all those buses traveling westbound on 495. That's not reverse commuters, that's the queue for most of those buses because of the capacity constraints for getting onto the XBL. And as you can see, and we'll be talking about this later in the presentation, when those buses queue, because there's no place else for them to queue, they're basically queuing in the general purpose lanes and creating problems for everyone else who needs to weave through them or across them or make their decision well upstream in order to avoid those queues. Okay, the exclusive bus lane approaches. So there are 3 approaches to the exclusive bus lane. The bus lane itself is the white line there along 495. I'd say about half the buses approach from the south. and used Turnpike Interchange 16E. That's the green line, and I don't have enough of a picture to show the queue. The bus queue extends through the toll plaza on a typical day. And what that means is that if you are not familiar with the area and you go through the right side of the plaza, you're really going to have a lot of trouble trying to exit to the local exit, which is to the left. And similar, you pass through on the toll plaza on the left side, you're going to have a lot of trouble getting to 495 and to get through the bus queue. Okay, the buses that I'm focused on, those are the ones coming from the north. That's the red line, and you can see the length of the line. That's the bus queue. The buses that we were looking before that were traveling 495 westbound, those are the ones that are coming from Route 3, and you can see the queue for those buses as well. So we've got a total of about 850 buses over the 4-hour morning period, and as I said, generally split 50%, 25-25 among the three approaches. All right, in developing the VISM network, obviously this was not the first VISM network that was ever developed for this area. We talked about there being multiple agencies involved here, and basically each agency had their own model. So I tried to follow the approach of, building on the work that was done before, but recognizing that no one was really focused before on Interchange 17, and certainly no one was focused before about the impact of the XBL queues. So enough network to cover the issues, but didn't want to be making the network any larger than it needed to be. Oh, and I should mention two constraints that are in the network, which are shown in red there. Those are a couple of weaving areas, which also limit the capacity of the roadway. 495 eastbound, where people coming from 16E versus 17E, from the south versus the north, have to weave through each other. And then 495 westbound, where traffic coming from Route 3 that wants to go to the Turnpike southbound has to weave through vehicles who are trying to get to the Turnpike northbound. All right, let me get into the couple of issues that I want to cover in the next few minutes of my presentation. Looking at the impact of the exclusive bus lane queues. Also looking at the impact of downstream congestion. As I mentioned before, the helix, the tunnel, the bus terminal, all of these things are bottlenecks in the system, and the queues from those bottlenecks spill back and impact this area that I'm trying to look at, which is, I guess, 2 to 2.5 miles upstream. Wanted to talk about calibration for overcapacity conditions, because I've been trying to be subtle with these pictures of both the previous pictures of the morning peak and this picture of the evening peak, that this is a roadway where the demand exceeds the capacity. And also talking a bit about those weaving areas, some of the approaches that I use, using conflict areas, using reduced speed areas. I didn't actually use dynamic assignment as part of this, but I was certainly in my toolbox in trying to calibrate this, and I wanted to talk a little bit about that as well. Okay, so the exclusive bus lanes and the courtesy gap. So on the left, we've got an aerial photo. We are taking a closer look at the Interchange 17 toll plaza. And what do we see happening for a few hours every morning on the Interchange 17 toll plaza? is you've got the bus queue, and these are vehicles looking to enter the exclusive bus lane, and the queue spills back through the toll plaza and then takes the right lane of the two-lane ramp as their queuing space. But the buses know and the autos know that in that one particular spot there, they don't queue there. They leave a gap so that vehicles who want to go to the local exit to the right know that they can pass through the plaza on the left side of the plaza and then weave across. I guess vehicles that don't know wind up getting stuck on 495, but in looking at kind of multiple pictures, this the gap is there, it's always in the same place. So now how do we model that gap? And BISM gives us many different ways of doing this. The way that I chose was to create a conflict area in that area where the autos looking to go to the local exit would have priority over the buses who would stop, and then would not enter the conflict area unless the bus could totally clear the gap area, so that no bus would ever be, the back of the bus would not be blocking any autos. And then what we see is a quick screenshot of the BISM network where we see the buses queued, we see the courtesy gap left open, and we see the autos sneaking through to get to the local exit. The other that I mentioned is the queue spillback from the tunnel and the helix, where that queue will spill back 1.5 miles or more, and eventually that queue spillback is impacting interchange 17, interchange 16E, as you can see on the photo, and we need to account for that in our network. But we don't want to be adding a lot of very complicated network in order to try to model what's going on downstream. So what I tried to do was to take advantage and use reduced speed areas in a way that I really hadn't used them before. Where reduced speed areas, typically you're using them for horizontal curves, you're using them for toll plazas, you're using them for turning movements at intersections, although I guess a lot of that is going away as well. But what I did here was I said, okay, let me set a reduced, and one of the beauties of reduced speed areas as well, as with so many other features, is that you're able to control the speed, but then you're also able to control the duration. So the reduced speed area can be in place for as much of the simulation as you want. The reduced speed area, you're also not limited to one area per section. They can overlap as long as they're operational at different times of the day. So what I did here was I said, okay, let me set a low reduced speed area during my warm-up period, and then once I reached I'll use the term equilibrium for lack of a better word at the start of my analysis period, and then from that point forward, I didn't want the reduced speed area to go away, but I would have it at a higher speed. And you know, there was really not, you know, how do you figure out what the timing should be? How do you figure out what the actual reduced speed should be? For me, it was just trial and error. Setting a couple of different speeds, seeing that, okay, I've got no congestion in my network. Well, the speeds are not low enough or the duration is not long enough. Running it again. Okay, now I got gridlock. All right, well, now my speeds are too low or my duration is too long. And then ultimately through trial and error, getting a situation where, I feel like my network is looking like it should, where I've got the right level of congestion visually, the right level of queuing through the network, and then I can check this by looking at the travel times through my network to make sure that's working as well. Getting that page down. All right, let me talk about model calibration and specifically model calibration when overcapacity conditions, when demand exceeds capacity. Because when you have that condition, you can't just be modeling or you can't just be calibrating to the traffic volumes, because the traffic volumes that you're measuring, they're not the demand, they're basically the capacity of the bottleneck. So, and I guess another challenge of this project is this project started, I guess 2-3 months before the start of the pandemic and didn't stop. So the idea of collecting new traffic data was really not an option. So what I had to do was to go back into these older, multiple older studies and try to extract out whatever existing pre-pandemic data there was. And okay, that's what I am going to calibrate to. And the additional challenge of that is you're calibrating to a combination of 2015, 2017, 2018 traffic volumes, different months of the year, data that you're, I guess, kind of questioning the quality of what you have, but you do the best you can. So in terms of matching the traffic volumes, everybody's familiar with the GEH statistic, target of less than 5. I felt I was working well there, except for that one location, which is a single lane. It's a portion of 495 westbound where in the morning, it's normally a 2-lane section, but in the morning, the bus lane is taken over one of the lanes. So there's only one lane there for traffic. And kind of whatever I could do with the parameters, I was never seeing more than 1,300 vehicles getting through on that section. There was a count from some other report that was claiming it was 1,700. At some point, I just found that really difficult to believe. So I said, okay, I'm good upstream at that point. My volumes are good downstream at that point. Need to move on and just accept it. The other issue, and one of the things that I'm always concerned about, is weaving areas. And collecting data for weaving areas so we know what the origins and destinations are through the weaving areas, because the 2 locations that I highlighted before, there would be arguably no congestion through those sections if nobody was weaving. It's really just the magnitude of the weaving volumes that are causing the congestion in the network. So one, you've got to collect, I'll say the OD data for the weaving section, and you got to incorporate that into your model. What I had here was I don't know if people have heard of SkyComp, which is one of the companies that Streetlight has put out of business. What they used to do, and I've been working with SkyComp since 1997, and what I think is the first project where they ever did this, used to go up in a fixed-wing aircraft and would just take pictures of the interchange. And then from the pictures, and this is in the pre-digital photo era, from the pictures, he was able to trace the travel patterns. And ultimately, he moved on to doing this from helicopters and digital photography and synchronizing multiple helicopters at one time. So at some point you could do a much larger area and get really good OD data. You know, getting OD data which is so important at the same time when you're doing your traffic counts and your travel times and everything else, which, you know, still an advantage over street light, but you know, it's just not, at some point, just not competitive anymore. Talking about the calibration, especially in an overcapacity condition, you want to be looking at the travel times and how they compare to the historic data. And as far as cues go, certainly looking at visual observations to make sure that your cues and your travel times, as well as your volumes, are all consistent with existing conditions. Let me just close with this, with the weaving section. Back in the day, and I've been thinking about this since I've been here the past couple of days and talking to other people. You know, my background was travel demand modeling and always creating OD matrices for those models. So when I got into traffic simulation modeling, okay, you have dynamic traffic assignment, yeah, you create a matrix, that's what I do, and that's how you run your models, using dynamic traffic assignment within the micro simulation. But for most locations, that's a really inefficient way of doing the work. So for this case, where I'll say the old Ken Hausman would have said, oh, it's a weaving area, you got to use dynamic traffic assignment in order to get it right. It's a simple weaving area. 2 origins, 2 destinations, static routes will work fine in this case. I think if you get into a more complicated weaving situation, or certainly, and I was really glad to see from the previous presentation about where you want to look at route diversion, that's really the place where dynamic traffic assignment for the micro simulation, you know, really has a role going forward. So that's my presentation. And if anybody would do a question.